In our list of types of integral domains, we've considered fields, PIDs, and UFDs. Now we want to consider Euclidean domains. So this is going to be an integral domain with a division algorithm. As usual, we're going to take a property of the integers to model our definition. So in the integers, we have long division. If I have a and b non-zero, then there exist integers q and r, such that a is equal to b times q plus r, with the absolute value of r strictly less than the absolute value of b. So q is the quotient, r is our remainder. From this follows the Euclidean algorithm, Bezout Identity, that the primes are equal to the irreducibles in the integers, and then we have the fundamental theorem of arithmetic. So unique factorization into primes. Now, we're also familiar with another Euclidean domain. So if k is a field, we can consider polynomials in X over K. Okay, and usually you've worked with K equal to the reals. So this has a division algorithm. This is just long division of polynomials. So I have f and g, okay, polynomials over K, g non-zero. Then there exists polynomials q and r, such that f is equal to q times g plus r, with the degree of r less than the degree of g. So with these two examples, okay, with the general definition of R an integral domain, we'll call R a Euclidean domain if there exists a function d. So this is going to be on the non-zero elements of R into the non-negative integers, the following two properties. So d of r is less than or equal to d of r times s, if r and s are non-zero. And there exists q and r, such that a is equal to q times b plus r, with either r equal to 0 or d of r strictly less than d of b. Okay, now note this is set up like this because we're not going to define d on 0. Now, the second property, okay, we're just modeling that after the integers and polynomials. What this first property says is just that if we take one of our elements and factor, okay, we want the factors to have smaller size than the product. Okay, so this d function is measuring either a distance or a size. For examples, we've already seen the integers. So here the d function is absolute value. For polynomials over a field, the d function is degree of the polynomial. For something new, we have the Gaussian integers, so z adjoin I. Here we have a subset of the complex plane. So for the d function, we're going to use modulus squared. Okay, we also call this capital N. So n of a plus bi is a squared plus b squared. Let's verify properties 1 and 2. For property 1, okay, we're working with complex numbers. So we always have that modulus squared preserves multiplication. So that means n of rs equals n of r times n of s. If we restrict the Gaussian integers, then we'll have, when r is non-zero, that a squared plus b squared is greater than or equal to 1. If r and s are non-zero, then n of rs equals n of r times n of s. N of s is greater than or equal to 1. So this is going to be greater than or equal to n of r. So that's what we want to show for property 1. As a side note, we know for Gaussian integers, r is a unit if and only if n of r is equal to 1. So r is equal to plus or minus 1 or plus or minus I. For property 2, we draw pictures. So we have m and n Gaussian integers. We have this equation, m equals qn plus r. So r is equal to m minus qn. We want to solve for q with d of r, d of m minus qn, strictly less than d of n. Now, how do we interpret this? So let's take a look. So what is m minus qn? So I'm going to start with n, and we're going to take multiples by all Gaussian integers. So we have m and n in the complex plane. I have n here. I'll multiply by I. So it's going to rotate us over by 90 degrees to in. Okay, so if I want all Gaussian integers in the product, I'm going to take all linear combinations of n and in over the integers. So it's going to give me a lattice. Parallelograms in this lattice are going to be squares. Okay, we have a right angle here. Now, to figure out what m minus qn is, what we're looking for to get this less than d of n, I want to find a point on the lattice that's distance less than, modulus n from m. Now, we can always find that. So if we draw one of these squares, I'm going to put in circles at each vertex. Radius for each of these circles is going to be the modulus of n. So when we put these in, we see we have coverage of the entire square. The entire square is covered. So that means m is going to be within one of these circles, which is going to be what we're looking for here. So then we pick that Q. Working more generally, we have the following theorem. Every Euclidean domain is a PID. For the proof, we use the same proof that we used for the integers. Now I want to show if I is an ideal, then I is generated by a single element. If I is not precisely 0, then there exists a non-zero B such that D of B is smallest. Then the ideal generated by B is contained in I. I want to show the other direction. So we'll pick A and I. Now, by Euclidean domain property, we can find Q and R that solves A equal to BQ plus R with R equal to 0 or D of R strictly less than D of B. Now, we have A is in our ideal. We have that BQ is in our ideal, so that means R is in the ideal. Because DB is minimized, that forces R to be equal to 0. So that means A is in the ideal generated by B, and that's what we wanted to show. So that gives our theorem. Now, we have a lot of consequences of being a PID. So here we have, Euclidean domain implies principal ideal domain. That implies unique factorization domain. We haven't proved that, but we've noted it. Then I have primes are going to be equal to the irreducibles. The maximal ideals are going to be generated by a single element, which is going to be irreducible. Then we also have, if I take R mod ideal generated by an irreducible, we have a field. Now, let's take a closer look at the UFD property. So if I'm in Gaussian integers, for instance, let's take an element like 8 minus I. So if we take D of this, we're using capital N, that's going to give me a 65, which factors as 13 times 5. Now recall, N preserves multiplication. So if I were able to factor 8 minus I, that would show up when we apply N. So we would have to be able to factor N of M1 times M2. Now, I have 13 times 5. They're primes, so I would have at most 2 factors here. To get a factor of 5, we don't have many options. The number way I can write 5 is a sum of squares. Somewhere in there, we're going to have a 1 and a 2. So let's try 2 plus I as a factor. So I'll divide that into 8 minus I. So to compute this, we're just going to rationalize the denominator. That's going to give me 3 minus 2i. So that means I can factor 8 minus I as 2 plus I times 3 minus 2i. Now note, if we take n of each of these, I get a 5 and a 13. They're primes, which means they don't factor any further. So that's going to give me our factorization of 8 minus I. Because we skipped the proof that PIDs are UFDs, let's show directly that Euclidean domains are UFDs. This will give us a chance to work with the definitions and to review factoring. Now, to start, we assume R is an integral domain. We'll say that A divides B if there exists some C in R such that B is equal to A times C. So this notion of divisibility is just reversing the language for multiplication. Straightforward to show. A divides B and B divides A. We can use the integral domain property to show that A is equal to U times B, where U is a unit. Next definition, greatest common divisor. So I'll choose A and B non-zero. We want the greatest common divisor of A and B, so here we'll call it D. For notation, we sometimes drop the GCD. Write it like this, which is supposed to be suggestive of the notation we use for ideals. D is going to satisfy. So 1, D divides A and D divides B. So D divides both A and B. Then if I have another divisor of A and B, say D prime, we have to have that D prime divides D. So D is going to be the greatest of all divisors. Now, because we're working in a general ring, this is only going to be defined up to a unit. if we focus on Euclidean domains, okay, the first step is the Euclidean algorithm. So this is going to let us compute greatest common divisors. Now the procedure is, okay, we have A and B non-zero. The Euclidean domain property says that I can find Q and R such that A is equal to Q times B plus R, where either D of R is 0 or D of R is strictly less than D of B. Now, we're going to repeatedly solve this equation, but we just shift our coefficients to the left by 1 with each step. So if we had A, B, R1 here, we move to B, R1, R2, we move to R1, R2, R3, and so on. Because D of the R's is strictly decreasing, eventually we're going to have to get an equation where a 0 comes out. And that's where we stop. Then the answer, the greatest common divisor, is going to be the last R that we compute. Now, that's a straightforward check with the definition. So let's check the two properties. If I want to show that, okay, greatest common divisor, so here it's R3, we'll show that that divides A and then it divides B. Now, from the last equation, okay, we have R3 divides R2. So I have R3 divides R3 and R2, which means it divides R1. R3 divides R2 and R1, so it divides B. That's one of them. R3 divides R1 and B, so it divides A. So that's our first condition. We just work up the equations. For the second property, we work down the equations. So let's suppose we have another divisor of A and B, say D prime. Well, D prime divides A and B, so it's going to divide R1, divides R1 and B, so it's going to divide R2, and then we just keep working our way down the list of equations. So at some point we're going to divide, in this case, R3. So that's our greatest common divisor, so that's going to be our condition 2. So that's what we want. Now, immediate consequence of the Euclidean algorithm is Bezout identity. So if we have A and B non-zero, then there exists I and J in a ring such that IA plus JB is equal to the greatest common divisor of AB. Now, this is just bookkeeping. So if we have these equations here from the Euclidean algorithm, this is just going to be multiplying and substituting so that I can remove all the R's except for the R3. So we'll get an equation that's in A, B, and R3. Since we skipped the proof that PIDs are UFDs, we'll show directly that Euclidean domains are UFDs. First, I want to show that the irreducibles and primes in a Euclidean domain are the same. Now, we'll call some definitions. So if A is a non-unit and non-zero, we call A prime if whenever A divides BC, we have either the A divides B or A divides C. Then we'll call A irreducible if whenever A is equal to B times C, we have either B or C as a unit. In a general ring, these two ideas are not the same, but we've seen if we're in an integral domain, then prime implies irreducible. And if we're in a UFD, irreducible implies prime. Now, we're not assuming the UFD property for Euclidean domains, so we want to show, okay, proposition, our Euclidean domain, that irreducible implies prime. So we pick our A, and then we want to show A divides BC, then either A divides B or A divides C. So let's assume that A does not divide B. Now, by assumption, okay, A divides BC, that means I can write BC as A times S for some S in the ring. We also have greatest common divisor of A and B is equal to 1. Okay, note here, because A is irreducible, the only divisors are 1 and A up to a unit. So since A does not divide B, greatest common divisor must be equal to 1. Now with that, we can invoke Bezout identity. So there exists I and J, such that IA plus JB equals 1. We multiply through by C, and then I replace BC with AS. Now, I can factor an A out of the left-hand side, and that shows that A divides C. And that's what we wanted to show. So in a Euclidean domain, the irreducibles and primes are the same. Now, I want to show that Euclidean domains are UFDs. So we need to show two things. First, for the non-zero elements, we have finite factorizations into primes. Then once we have that, we want to show that this factorization is unique up to units. For part one, we'll need the following lemma. So note, this is the first time we encounter condition 1 in the definition of Euclidean domain. So condition 1 is going to guarantee the UFD property. Now, R is Euclidean domain. We have A and B non-zero, B not a unit. Then D of A is strictly less than D of AB. Now, condition 1 is just this statement here, but we have less than or equals. So what we're trying to show here is that the inequality is strict when we have these conditions. Now, recall our proof that Euclidean domains are PIDs. What I want to do, I want to form the ideal generated by A. So from our PID proof, what we had, A is going to minimize, okay, the D function among all non-zero R in I. So that means, okay, since AB is also an I, okay, we have that AB is a multiple of A. If we had that D of A was equal to D of AB, then we'd have the AB generates I also, okay, because that still minimizes the D function. So I would have these two ideals are equal, and that would mean that A is equal to AB times S for some S in the ring. But by the cancellation law, we can remove the A's. We have BS equals 1, and B is a unit, which will be a contradiction. So that shows our lemma. To show existence, we use induction on D of A, where A is non-zero. For the base case, we use the elements with the smallest D of A. It's equal to D of 1, and these are going to be the units. Now, what is D of 1? Well, that'll depend on the Euclidean domain. For the integers, or Gaussian integers, D of 1 is 1. For polynomials over a field, D of 1 is 0, the degree of a constant function. Now, the claim is U is a unit if and only if D of U is equal to D1. Then, in the base case, we're just considering the units, and these have a trivial factorization. Now, by the lemma, D1 is strictly less than DB for B a non-unit, so I just need to check what D of is on a unit. Now, by condition 1 in the definition of Euclidean domain, D1 is less than or equal to D of 1 times U, which is DU. In the other direction, DU is less than or equal to D of U inverse, which is D1. So these are equal, and the claim holds. Now, for the induction step, I'm going to suppose there exists a finite factorization when D of A is less than or equal to K. So here I'm using complete induction. I'm not just assuming a single statement, we're assuming a set of statements. We suppose D of A is equal to K plus 1. Then two things can happen. Either A is a prime and we're finished, or I can write A as B times C with B and C non-units. And here we're interchanging prime and irreducible. Now by the lemma, we have that D of B is strictly less than D of A, D of C is strictly less than D of A, so the induction hypothesis applies to B and C. So B and C have finite factorizations. When we put them together, we get a finite factorization for A. So that's the induction step, and that's the induction proof. So we have existence. For uniqueness, okay, we just give a sketch of the proof. You can build an induction proof around these ideas. So let's assume A is non-zero, and we have two factorizations into primes. So I'll pick a prime on the left-hand side, say P1. By the prime property, P1 is going to divide some Qi. Now, because these are both primes, we have the Q of I. It's going to be equal to P1 times U with U a unit. We tally both of these. We apply the cancellation law. That's going to lower the number of primes on each side by 1. And then we're just going to keep repeating this process, which must end in unit equals unit. So that's going to tally all the primes that occur. And we note that the number of primes on each side are equal. So that's our uniqueness proof, and you can put the induction together from that. Now, what's coming up, we have the general theory here So now we just want to look at specific cases. So we'll look at primes in the Gaussian integers, and we'll look at primes in polynomials over a field.